Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, thank you for joining us this afternoon. This is the session around semantics. We had one this morning, and this afternoon we have 3 speakers. And we're going to start with our first speaker, Carlos Pedrinacci from the Open University UK.
Thanks, Evelyne. Hi, so I work at the Knowledge Media Institute at the Open University back in the UK. And I'm going to be presenting the work that we're doing in the context of a project called VPA Share, using semantics and services to actually support the Virtual Physiological Human. That's a project that was previously mentioned during the keynote this morning. So just to put you into context, what is the Virtual Physiological Human? So the idea is to provide both a methodological and a technological framework which would allow people basically to perform collaborative investigation on top of medical data and so on. And the notion underlying it is that it views the body, the human body, as a complex system. And therefore, you need to have a global, comprehensive view of the whole body in order to be able to better support decision-making or even advancing research in the medical sciences. So some of the challenges that the VPH approach has to deal with are some of the common problems that you have with all the big data situations, where basically you need to access to large quantities of data, distributed, heterogeneous, but then some other aspects which are somewhat more specific to that particular domain is the need for having somehow composable models that could allow scientists to create new workflows, new analysis means for to run over the data that they have in order to come up with new conclusions. And another important activity that they need to carry out in this domain is actually the evaluation of theories. So once you have a theory, can you actually run it, well, test it against the data that you actually have in order to know whether this is true or not. So these are some of the challenges that the VPH community as a whole has to target. Now, how does it look like in concrete scenarios? I'm reusing this slide from the project, where we have 4 main workflows that are actually the driving forces somehow giving us the use cases, the concrete examples where the infrastructure that is being developed has to excel. So you typically, what you have is you have large quantities of clinical or biomedical data spread across different organizations, different formats, distributed all over the place. And then what you want to do is to be able to analyze this data in order to get some conclusions. So what you do is you essentially create some models that you typically have to personalize to the concrete analysis that you want to carry out, or the concrete patient you are dealing with. You then get the data, run the workflow, and get your conclusions, which in the case of this domain can be typically, well, a diagnosis or a treatment suggestion, and so on and so forth. The workflows that we are contemplating at the moment, so there's one on aneurysm analysis, there's another one on HIV, and so on. They have obviously their own concrete, tiny details that make them different in the kinds of data they're handling, the formats they need to deal with, and so on. So we have to deal with images of segmentations of brains and bones and so on. In the case of the viral lab use case, we even have to deal from, we cover from the gene level up to the social network analysis. So how do we, how is this approach in the project? So the view of the project is essentially to provide an integrated, comprehensive infrastructure that covers from the cloud level, where we have all the high-performance computing infrastructure put at the hands of the researchers, On top of this, we have obviously services for providing access to these computational resources, the data, and so on. And then we increase in the level of abstraction, and we want to provide a knowledge level access over this data in order to better support people in finding the information, intermixing it, integrating it, or even running some inference services on top of these to, for example, analyze a concrete patient and derive whether it's, it's going to have a concrete disease in terms of probabilities and so on. On top of all this, we have a set of integrated user interface tools that, although it's a typical scenario where you have to kind of provide access to the underlying IT infrastructure, in this case is particularly sensitive because the users that you get are people that they don't want to deal with complicated stuff. They just want to do their work. This is what matters, and anything that would deviate them from their actual practice, their day-to-day work, would be a problem. Peter in the keynote was actually mentioning that if you have, the number of clicks was actually affecting a lot on the usability of these tools and the actual take-up. I'm going to be focusing on this talk on this third layer, given that this is the session on semantics, and in particular, I will focus more especially on the services side. Leaving the other aspects to my colleagues that will be presenting afterwards. So the first part of the work is we're working on is on creating a web of VPH data. So, like I said, in the setting we have clinics, we have researchers, we have different kinds of reports, Excel spreadsheets, CSVs, images of different zillions of formats that we have to provide access to. And this is an explosion really of data in quantity, but also in heterogeneity and distribution across different settings. The approach that we're following is one that somehow we were hearing in the previous session. So what we're doing is we're using the linked data approach that comes somehow from the research on the semantic web, to be able to structure this data, represent it in RDF, so that it can be better integrated and interpreted by software, but also it can be interlinked. So what we are looking at is trying to create a web of data about the virtual physiological human that computers could better use for carrying out their analysis. I'm making particular emphasis here on this part, the pink side of the image, which is actually already existing data of this kind, or that is relevant of this kind to this domain. And the idea that we have is essentially to create with our data a similar kind of distributed linked data structure, gathering all the information, but also interlinking it to existing data sets so that you could actually correlate it, enrich it, and benefit from all each other's work. Now, in order to do this, I'm not going to cover the details that Karin was presenting previously, but we have to do the typical activities, like providing some vocabularies. Here we're working essentially on providing some modular vocabularies that allow people to capture what they, in the domain, they call archetypes. For the ontology-aware people, that would be ontology design patterns, in a sense. But essentially, we provide small vocabularies that cover part of the descriptions that we have to cover, like measurements or like treatments or like diagnosis. And these become, modular, pluggable vocabularies that you can use to describe and to, basically to present your data in a semantic form. Obviously, we have to work, like I said, a lot on assisting people. So a lot of work is being put on trying to help the users in actually selecting these ontologies. The approach that we're following at the moment is obviously informed by existing services in analyzing the quality of ontologies and so on. But one particular emphasis that we're doing is trying to restrict this subset of vocabularies so that at least within the VPH share community, that improves the reuse and the integration across, obviously within the project, but also across different projects working on the same activities. And then obviously we have the necessary interlinking, mapping, and indexing. So these are the typical activities that you have to carry out to expose your data as linked data. Now, in this particular case, there are some outstanding issues. One very important that hits us every single day, basically, at every single discussion that we have, is privacy. We're dealing with particularly sensitive data. It's data about patients, and therefore it has to be anonymized. But you have to bear in mind, like I was saying before, is that data is owned by different actors, which have, all of them, they're legally bound. So they have legal requirements with respect to this data. And therefore, you cannot just simply publish it like this. So you have to anonymize it. And typically, this anonymization has to happen before it actually goes at the integration level. And that makes it particularly difficult, for example, when you want to do interlinking across data sets to say, for example, this health record here is the same, is about the same person as the health record over there. So traditional techniques from the linked data world, which basically use some heuristics to do a named entity, entities recognition and interlinking, are not directly applicable here. So in this situation, we necessarily will hit or will be in a situation where we have coexistence of different unique identifiers for or referring to the same entity. As you recall from the previous presentation, for those that didn't come, one of the core principles of linked data is that every single entity, every single thing that you're referring to in your data should have a URI, a unique URI. And therefore, having different URIs for referring to the same thing brings some additional difficulties in this particular case. Another thing is obviously regarding the heterogeneity of the data, but this is, again, one common problem to all the data-intensive scenarios. Okay, so coming to the services, which is where I want to put more emphasis on this talk, is so what we're doing is we're applying services, in particular linked services research, to actually support this concrete scenario. So the overall evolution of the research being carried out and we build upon is that essentially services viewed as black boxes that provides a certain reusable functionality that you can plug into your system so that you can basically reuse across different settings, are very valuable, but they have a typical problem, which is typically they are expressed in terms of string float, like in this example, which basically tells you the data type, but it doesn't tell you the semantics. So the Semantic Web Services community came into play and said, well, we need to provide semantics to these services, so let's add annotations to those, saying what these actual inputs and outputs actually refer to. So there was quite some work on this area, mainly two main communities. Well, three main communities would be the OWLS, the WSMO community, and the WSTLS that later on became a standard as SOSTL. They were all working on providing these annotations to these services. Now, that work was somewhat pre-linked data, and they were in many cases using ontologies that were enclosed within concrete settings, within concrete organizations. And therefore, integration, although it was improved, it was really remained as a enclosed within a concrete particular application. That's one issue. A second issue that this kind of research hit was that it was predicated on, reaching the maximum expressivity that you could. And that has obviously the obvious advantage that the more expressive your framework is, the more things you can do and in an automated manner. But it has the added problem, which is complexity in terms of the computational overhead for processing these descriptions, but most importantly, perhaps, overhead for the actual people that have to provide these annotations. Coming up with highly rich annotations of these services was a particular overhead, a particular issue. So what we're doing in this linked services research is following up on this idea of annotating services to provide a characterization from a semantic perspective of the services used, but following a linked data approach. So what we're doing is any vocabulary that we use for describing these services is taken from the web of data, which ensures us that first, it's based on the, linked data principles. You can go out there, get the descriptions and so on, but it also has existing data sets that are providing data in this manner, which actually turns these services into more reusable, simply because they can be applied over the data that is already existing on the web of data. So if you have a data set providing genes descriptions and you're using the same vocabulary for actually describing your service, you would be able to directly feed this kind of data into this service, making this data more useful and the service also more applicable. And in fact, one of the issues that Karin was also highlighting in the previous talk is that making use or making the most out of linked data is still an ongoing research issue. And this is in fact the approach that we are applying towards supporting the processing of this data. So what are these linked services? So linked services essentially are services described as linked data. So what do we describe? We describe their inputs, we describe their outputs, the functionality, we can also cover non-functional properties and so on. But essentially, we are describing this as linked data. So you have RDF triples that are describing what the service is, and these RDF triples, they are published on the web of data in the same manner as linked data is published. And that has the added advantage that basically descriptions of reusable pieces of software, descriptions of reusable services, metadata about these services is coexisting with the data. So you can, when you are developing your application, move across between the data and the processing layer smoothly because you have this integrated approach. But we'll see this in more concrete detail afterwards. And what we do is essentially we provide infrastructure so that these linked services can be seen as linked data producers. So you put it on top of existing data resources and you are generating linked data, but also consumers. So you could grab, suck in data from the web of data, process it, and generate some new data back. So these linked services are playing in the project two main roles. One is the controlled publication of data as linked data on demand, and I'm going to explain why we are doing this in the project. And the other role is for supporting the creation, so for better supporting the creation of VPH workflows, using linked services as the core activities that you actually interleave, that you actually orchestrate to achieve your concrete analysis. Why do we use linked services for accessing the data on demand? Well, like I said before, privacy is a very important issue in that particular domain because you have very sensitive data. And essentially, these organizations, they don't want to let any piece of data go out without it being properly anonymized and secured. And therefore, they establish control access at their boundaries. So the typical, let's say, approach that is contemplated in the linked data world, where you have a Sparkle endpoint that provides you access for querying directly this data, is no longer viable. What they do is they provide typically a service-based interface on top of this, which provides control access. So you have to ensure that you are properly authorized, that the data is properly anonymized, and then you can access the data. So what we do is, because we have these services, we provide annotations of those services, reusing vocabularies, and on the fly, we have infrastructure that based on these descriptions, based on the data that these services provide upon a request, we generate linked data. We're going to see a concrete detail afterwards. So going back to the previous picture where we have all this data explosion with different kinds of data types, data sets, and so on, what we essentially do is we provide service descriptions, service annotations, semantic web link services sitting on top of these data sets that are enclosed within the organizations. These have declarative descriptions about how to actually interact with these services, or how to actually craft a request. May it be a RESTful service, or may it be a WSDL kind of service. So it actually tells you how you should invoke the service, but it also tells you how you should transform the XML, JSON, or whatever kind of data you're getting from here into RDF that you can publish afterwards. So these semantic descriptions provide us already this kind of level of abstraction in which it allows us to see all these data mess, let's say, as a more structured approach, interlinked in linked data terms. And then eventually, once we have this data, what we are doing in our research is essentially, okay, now we have all this linked data. Let's support people in defining their workflows. Let's support people in actually modeling their clinical workflows to, I don't know, do some diagnosis or whatever they are interested in on top of this data. And this is what the top layer indicates. So essentially, workflows are no longer they no longer have to deal with the intricacies of different underlying database systems, different underlying XML formats, CSVs, and so on. What they have to deal is only with linked data, which is essentially data that is described in terms of reusable REFS vocabularies. It's interlinked, and actually these workflows can reuse this data to perform their analysis. So in a sense, once we've done the exposition of these data sources, we just view the world in this manner. Reality, sometimes it's a bit more complicated because many times they don't even use standard formats for the description of, for the provisioning of the data sets. But that's the way we view the creation of workflows in this project. So a concrete example to give you a hint about on what it means to do workflows on this manner, in this way, and how that can be beneficial to actually a researcher doing whatever it's doing within his day-to-day work. So let's imagine a workflow here where we're dealing with patients that have HIV. So what we want to do is to start with getting a sample of all the patients we know of that actually have HIV. Because we're dealing with linked data, that essentially boils down to throwing a Sparkle query, certainly more complicated than this one, but this is just to give a hint, which would be going to the different data sets we know have data about patients, asking for those that have actually been diagnosed with HIV, and sucking the data out. Now that we have this, we can actually do in the next step is also in the same way that we're looking for data, we can look for services, because at the end of the day, like I said, any of these linked services is also published as linked data out there. So what we're doing is we can actually ask within the workflow, find me all the applicable treatment suggestion services that you know of. You get the metadata about them directly from the existing data sets out there in the cloud, and then you can directly invoke. Let's remind that we have these declarative descriptions of these services, and therefore we can invoke them on the fly. So that's how we can turn these workflows that usually have to deal with lots of intricate details of the actual formats, details, and so on, to more dynamic workflows that can throw semantic queries to distributed settings, benefit from the interlinking between data sets, but also do actually the binding to concrete services at runtime on the basis of what there is. So if a new researcher comes along and provides a new service that does treatment suggestion, which is better than any other one, you don't have to modify your workflow, because your workflow will still be able to go out, look out for those treatment suggestion services, bring it up, and execute it automatically. So how do we support this? Well, we have quite a lot of infrastructure providing this. The first step, obviously, is authoring of this description. So we have tools for, what you see here is a tool for annotating web APIs. So you can grab the web API description. Typically, there's an HTML page describing it. That's as far as you get. You can grab it and annotate it. What we're using behind the scenes is we're using the web of data as background knowledge. So here we're interacting with Watson to actually get suggestions about possible vocabularies that we can use for annotating this service. So we have selected here the population. We're interacting with Watson, getting some of the relevant ontologies that we can use. Once we have annotated the services like this, we can submit it to a registry. That's what we call here iServe, which is essentially a registry for linked services. What this machinery does, essentially, it provides you support for grabbing any document describing services, maybe an HTML web page with these annotations that we provide, or a WSDL service with the descriptions, suck it into the machinery, and automatically generate the right RDF triples to actually expose this in the linked data cloud. And in fact, it's already part of the linked data cloud, providing its own Sparkle endpoint and so on. Obviously, doing advanced discovery of services goes beyond this. So what we're doing is we're going beyond this. So we provide Sparkle-based discovery, but that's as far as Sparkle can go. So you can use some basic subsumption reasoning if there is the machinery behind the scenes allows for it. But then we have embedded algorithms that are provided through a simple RESTful API for doing input and output based discovery using RDFS reasoning. We also have support for functional classifications and also similarity analysis. And then we have machinery for composing all these discoveries. So we could ask for services that are of this kind, say treatment suggestion service, that have this kind of input but do not have this kind of output, and so on. So you could compose them to discover whatever you want, and you can do this at runtime within your workflow. We obviously have support also for invoking. So we have this. We have a generic engine called Omnivoke that, based on these declarative descriptions of the services, based on these annotations that we publish in the cloud with iServe, you can feed it with it, and you can say, I want to invoke these services, and this is my input. And the input that you can provide to it is directly RDF. So you could go to a data set, Freebase in the examples by Don, for example. You can go to Freebase, get some data, feed it in, and the engine will take care of checking that the declarative description and the input that you're getting actually match, and then doing the transformations, generating the actual invocation stuff behind the scenes, talking to the service, getting the results back. And what you get back, again, is RDF out. And what we're doing at the moment at this level is we're actually injecting Provenance, which actually hooks pretty well into the following talk. So what we're doing at this level is, because services are already described, are entities that are described as linked data in there, what we're doing is we're injecting, anytime we are generating some data that comes out of the execution of some service, we are injecting this Provenance information for it. And just to somehow to conclude, another example of work that we've done on top of these descriptions together with our colleagues from Sheffield, and that shows the value of having the descriptions of services published also in the linked data cloud, is that we've worked on supporting the recommendation of services. In particular, we've done collaborative filtering, but in this case we're doing content-based filtering for services. And what we have done in this case is that we know that a concrete person that has certain interests, because we know data about this person that comes from the data cloud, is actually might be interested in this service because he's interested in music. We know that music is actually a subset of this kind of music, which is the actual annotation that was used for describing this service. And thanks to this, you can actually follow the links in the data cloud to actually provide advanced recommendation that you wouldn't be able to provide otherwise, because you're exploiting the web of data as background knowledge. So to conclude, in the future, we're going to be obviously working on embedding these link services, invocation infrastructure within a workflow engine. That's part of the project, which has been running for 1 year for now. We're looking into Taverna as the example, but that's not particularly restrictive. And then obviously we have to work a lot on better supporting the annotation of these services by humans, because in this particular domain this is particularly important. And then finally some work on cross-ontology, logic-based discovery of services. So that was it from my side. Thank you for your attention.
Question? So hold on, just give you the mic for the recording.
Yeah, I wonder how you deal with the change of your data if you publish your data into linked data. What if your underlying data is changed?
So the way that we're doing this in the project, because of the restrictions that we have, is we essentially are providing views over the data underlying it. So whenever you're actually requesting for data, we are getting it, and returning you the RDF for it. So we're not materializing the data beforehand.
Okay.
Essentially, because we don't have read-write access to this, to the underlying systems. Mainly because, like I said, there's a lot of organizations that are legally bound, so they will never allow you to have write access to this data. So they control this, and what we provide are views, linked data views over this data at runtime on demand.
Okay. Okay. Thank you.
Thank you. While you set up, I have a question. Mm-hmm. So, how do you measure progress, or how do you evaluate such a system? What are your metrics? Do you have metrics? And it's a complex.
For which part of it? The whole the project per se, or the whole infrastructure for supporting the creation of applications?
Well, I mean, tell me, you know, I mean, I'm interested in both, but in the interest of time, just, you know, tell me, select one, and I'm just curious about, you know, how do you define, what type of metrics do you use?
So for this infrastructure, the main issue is that, well, our main goal is to better support the creation of applications on top of structured data. And therefore, the metric for this is, you know, to which extent are you improving this? And essentially, there you run into evaluation studies of the things that you can or cannot do, and then obviously that has to be run over time. But one simple metric to show the, let's say, advanced support that we provide, and the advantages is that up until now, for example, when you're dealing with web APIs, you always have to create a concrete ad hoc client. And the same was happening in this scenario. You always have to come up, create ad hoc client for supporting the access to the data set and so on. With this work, what you do is, in order to provide access to any concrete data set or any concrete service behind the scenes, you only have to provide a description. You don't have to do all the implementation that goes behind the scenes, so you save time in there.
So easy, yes.
Yeah.
Okay. Okay, thank you.
Thank you.
Okay, so our next speaker is Stefan. Oh, okay, we need to exchange mics. So our next speaker is Stefan Staab from the University of Koblenz, who is going to talk about provenance.
Thanks a lot. So it's quite a while ago that Evelyne asked me to give a talk, and I said, okay, I talk about provenance in the semantic web. Then she told me that I don't have 2 hours, but just 20 minutes. So what I really wanted to do originally was to tell a bit about provenance in the semantic web. When you have data and you query and you pull data together. And you pull data together from different sources, just like in the scenario just described. And then you might want to know, well, actually, where did it come from? Or what kind of trust is associated with that? Or when was that last set or last modified? And all that kind of thing which we subsume under provenance, which may involve quite a fancy querying and inferencing on top of that provenance data. And then I wanted to talk about policies and obligations. And then with the 20 minutes, I just decided to scrap this. And therefore scrap the title. And therefore say, today I want to talk about policies and provenance for data management. And that means basically the two questions of what may I do with your data and what do I have to do with your data. And the motivation for this came from some incidents. And you might have heard about them. So the first incident was that a couple of years ago, the CIA published the list of the agents on the web. Well, it's a very clever move, right? If you have a list of secret agents and you publish them on the web so everyone can access the list and know who the secret agents are. That was one thing. Another thing which was also quite interesting, I think also a couple of years ago, the Italian tax office published basically all the tax data on the web, which in some countries like Sweden I think is quite common, but in other countries like Germany or Italy is not so common, at least not allowed by law. So again, what makes this interesting, these two cases, is that we don't have a hostile environment. We have an entirely friendly environment of people managing data and putting it in the wrong place. So it doesn't really have to do with access rights, right? Because those people who published the data had access rights. They didn't fight against the system. They just used the system in an undesirable way. So allowing or disallowing data handling has not only to do with access rights. So I fully agree with what Carlos just said. And I would say, yes, let's build on top of that. But we need to do more. That's basically what I'm saying here. So our assumptions, and we've heard it about them in these sessions, by Karin, by Carlos, by others who talked about using the semantic web, for example, in archaeology. Why assume that our data is available in some common data format. Semantic Web, we often have flexible graph data, ontologies as some icing on the cake, if you like. We also look at how can we do provenance in OWL, and if you are interested in a specific aspect, you can do this actually quite efficiently sometimes. And then we want to have this great infrastructure to share data all over the place, distribute, republish, query, replicate. And then, of course, we have questions like the ones I just raised with these examples. And then you think, well, but doesn't this work? I mean, if I look for Facebook, I can say, I want to share this photo with Evelyne, but not with Carlos, right? Yes, I can do it, but it's very inflexible. I cannot say, I want to share the photo with all people who attended this workshop session, right? That would be maybe natural because they saw each other, so it's not really a secret that they were at this session, while maybe some other spouses so shouldn't know, I don't know. So we can give these limitations, but we want more. And what we thought would be quite nice to have, are some sort of business rules. I mean, they are typically called business rules in some environments, but they don't need to deal with business. They can be rules for handling these access rights in a very flexible manner. Now, let me put this a little bit in a scenario that may be more familiar with you in the eScience. For example, a hospital, right? And in a hospital, you have typical things like you may have a physician and handling some patient. Here, the patient would be Jane Doe. There may be some nurses, and then you have a distribution of things to do. And of course, this may happen even across different systems. It can be one centralized system, it can be several systems. And then in this tiny toy example, the physician may discharge the patient and transfer the data about the patient to the nurse for the nurse to handle. And then maybe that should be transferred to the patient. Or maybe not. That's exactly the question. That's exactly the kind of policy the hospital has to formulate, maybe together with some ethics committee who should see the data. And of course, the patient should have a say, at least according to the EU regulations. And what we would like the patient to do is to say, well, I want to describe what you may do with my data. You may, for example, use it for research, for eScience research, as soon as it's anonymized. But maybe I only want to share parts of my data. So yes, I want to share those part of my data about my broken leg, but not about my my psychic condition, for example. Yeah. So it may be a bit more refined what you want to share or not. And I also want to tell you a bit about what you must do with my data. For example, I say, okay, you can do it for, you can use it for research, but if a research organization uses it, it should not give it away further, so it may not be linked further, and you have to delete it after a year. So I'm sure that if I come back after a year, then this is also closed, and you cannot link too much. And actually, that's a concern right now, because we're in the semantic web. We're all about linking data. But some people, I've talked to a couple of people who are very concerned about linking data in a rather unpredictable manner. That, and we know the old story. We heard them also yesterday. I think it was yesterday again. That at some point you may come back and then do some inference about this data having been linked, and you may do some interesting inferences about people. So let me talk first about the issue of what may be done with my data. And so we have one approach that I want to present at some higher level called PAPL. So the very same setting, you do some things, and that what you do here and what you store here, that's basically our provenance, right? You can have all kinds of provenance models. We basically built an open provenance model, but you could choose another one. And then at some point you want to do a step, and you have to ask, am I allowed to do this? For example, to give it from the inside to the outside, even if this outside may exactly be the patient. So staff members maybe have this kind of rule. Staff members are permitted to transfer the record to the patient after her discharge. Maybe, perhaps not before. for whatever kind of reasons. Maybe you don't want the patient to go away, go to the next hospital after you have invested some money, and the next hospital can treat her for less money. There can be all kinds of rules because of which you might want to do something or not. And what is interesting about these kind of rules is that they, of course, have to do with data, they have to do with the data. They quite often they have to do what happened in the past, right? Has the data been anonymized? Has a certain action taken place? So quite often you need to refer to something like, has this happened before? Or has some things happened in a particular order? So what is stored in the provenance is not just arbitrary knowledge, but it takes a special status. And of course, well, that's how we write it down in the paper. In the system, we write it down as RDF, but this way is very easy to communicate. So we just say, well, one step in the provenance record is about a piece of data, records Jane Doe. There are some people involved in doing that, like the physician and the nurse, and they want to transfer something. And there's some provenance history that's indicated here as a graph. And for writing it down, we just give it some IDs, whatever the IDs are. Here, they're for simplicity, they're just numbers. So that's basically the history that we use. And then we are at that point, and we want to decide, should we give it further, or should we rather keep the data, or do something else with it? So that's the problem where the policies come into play, and policies must decide according to the history of the data. Now, if you take typical policy languages, like XACML, EPOL, XRML, they're mostly focusing on static data, like who's the actor, what time do we have now, or what type of data do we have. And what we added was exactly this piece of information, which is quite crucial, but also not so easy to handle because it involves aspects of time and ordering, about the provenance and the history. When you do that, then it becomes actually quite easy to provide a rule language, and here basic syntax for this rule language. It says basically permit some step with the ID to happen if some condition is fulfilled or you deny it. That's all. And then you just have some set of operators where you say, I allow some transfer in some step after some discharge has happened, and it's only allowed if actually the person who wants to do the transfer is actually a staff member. Not everyone can come, or not the patient may decide this herself. So basically what you write down is you write down your policy, and it's quite easy, straightforward to provide this there. And then you may decide at this point, the transfer is allowed. Okay, so you ask this question, and what you then need to answer this question is basically all the facts. That means the history plus the next step. And the history may include things like that has happened to data. It may also include attributive information. So you may decide to provide state changes in the histories that do not directly concern the data, but that just reflect that some modification was done and that represent this. So you have something actually quite more than just the steps that have happened. Then you ask about the step that should be done or not. Then you take all the policy rules. Here is just one, but it could be an arbitrary combination of permit and deny rules, in which you formulate your business rules. And then you get back basically to the question whether this step that you want to look at here, step number 7, is allowed or not. And then you can do the corresponding action. You see, there's nothing here about the access right enforcement. It's only a question now whether you can do it or not. In that sense, it's also still, at this point, rather a system engineering setting, because, I mean, having some general data log implementation of that is quite straightforward. But the core question, of course, is to make these rules formalizable in a way that's still useful for not only the expert programmer. And once you try to do this in pure data log, then you run into issues of understanding what's happening. Okay? So the other part, the other idea was then to say, now we can easily write down some business rules and ask this question of whether I can publish, or whether I can publish my list of CIA agents on the web. And but the other question was then, when you look at these policy languages like XACML, that don't have actually a formal definition, which is a bit funny. So XACML says you have permit and deny rules and have obligations, and does not really specify what it means that something is permitted or denied, or that you have an obligation. So we thought, what about these applications? They are very interested because they affect the future. I say that something is supposed to happen. When I finish my treatment, I want to get my dossier in order to store it for myself or give it to the next practitioner. So the idea was to look not only into the past, into the provenance of data, but also into the possible future of data, and see what we can infer about the future. Okay, let's look at the very same scenario. We have some discharge and then some transfer to the nurse, and then the nurse may decide to transfer to Jane or not. And we may look at several policies. First policy being staff members are permitted to transfer the record to Jane Doe after her discharge. And staff members and the archive are permitted to transfer the record to other staff members. So you can move the data around in the hospital. And we also have two obligations here. The first obligation is that Jane Doe demands to receive her data record after her discharge. So she wants to get her dossier, basically. And the nurse has to transfer the record to the archive. Well, if it's done, once the patient has been discharged, the archive should have all the data for later usage. And well, here just for the sake of having a very short argument, we have a deny rule. Let's say the patient should not give data directly to the hospital because the hospital might not actually trust the data. So what's happening when you have these policies? So the first kind of policies, the permit rules and also this deny rule, regulates what kind of activities can happen in which kind of ordering. The obligations state that in the future something must happen. Now, what are the problems with these obligations? Well, if I have an obligation, I may do a step that makes the fulfillment of this obligation impossible, right? So if we talk here about, for example, archiving something, if you delete a piece of data, you can no longer archive it. So when you do the one step, you forbid the other step. But if you look at permit and deny rules, the rule is not to not delete data. Obviously, you want to delete some data. But the rule is that it should eventually be archived. And in this scenario here, it's not only that maybe we don't want some deletion because then we have immediate violation of some obligation, but it can be a bit more tricky. What we see in these two obligations is that we should have a transfer for the dossier to Jane Doe and to the archive. And at the same time, when we have it with one person or with the archive, we cannot give it to the other, at least not directly. So we have obligations that do not play together automatically. So what is the solution to that? Well, this obligation, this ordering here would not work. So transferring it to the nurse transfers it to the archive would fulfill the first obligation. But then transferring it to Jane Doe is not possible because the archive is not supposed to be to anyone, basically, other than staff members. What would work is a transfer to the archive. Then from the archive, a physician could retrieve it. Maybe this would a little bit be inconvenient here, but it makes the example nice and short. And then the second obligation could be fulfilled that Jane Doe gets her dossier. So what we see here is that depending on business rules, you allow and disallow things, and you state what should be fulfilled in the future. The question is, when you do such a kind of step somewhere as the next step, can you fulfill all your obligations in the future? So we model this basically as an extension of provenance. The provenance is part of the history. So you have all different types of steps happening in the history. And then you're at this point now. And then you have continuation of the past into the future. When we look at the example, we see that there are some steps actually that are all green, meaning here they are allowed and they don't violate obligations in a foreseeable manner. And of course, we may have these red arrows, maybe things that are completely disallowed because they would immediately violate our permit or deny rules in some way. And or they may lead to a problem in the future by no matter how you go in the future, you could not fulfill your obligations any longer. So this right part is what we call the future execution graph, or this is the provenance or the history of our process. So what we are then interested in is what we call the closing. And the closing is here, this yellow part, where we look at what are those steps that close our obligations. Obligations are triggered. If I have a patient and I have the rule to give the dossier to the patient in the end, then the moment I have a patient admitted and a record being created, I have an obligation at this very moment. This obligation may have been triggered somewhere in the past. For example, at this point here, well, here it says patient has been examined, record created. Now I have the obligation. And this obligation is open. It's open until all necessary steps have been done to fulfill it. Of course, we can have 1, 0, 1, or many obligations. And what we look for now are valid paths in the future that are allowed and that close off all my obligations. And if we look at those paths in the future, that's what we call the destiny of our data. That's where it should go, right? So we should avoid all those paths that violate things, and we should pursue those paths that make sure that we don't do anything disallowed and that we can still do what we must do in the future. So this part here is what we call the destiny. And the question is that if I do certain things, whether my whole system and the data in my system has such a destiny. So what we do here is basically say that if we do a next step, hypothetically, does such a destiny for the rest of the system and the rest of the lifetime of the system exist or not? So we have a yes/no question that we can ask here. So here at this point, we should ask, does this step have a destiny? And does this step have a destiny? According to our model, this step does not, because the dossier will never get back into the archive. This step has a destiny because the archive might give it to the doctor, or who might give it to the patient. And of course, you see that it's nothing that you would see immediately in one step, because it's way too indirect. What do you do here? Well, you do the same thing as with the permit and deny rules. You take all the history, you take the step in question, you take all your policies and obligations. What we need to add here are axioms specifying possible steps. There are some things that are impossible. So if I delete a data item, I can no longer work with it. I can no longer transfer it. This seems like a very open end, but indeed it isn't. We have basically 7 categories of things that are done to data, which are quite common ones, like creating them, deleting them, updating them. Of course, some of them are more or less transparent. You can refine them. You can have more specific steps, and you may decide to add further axioms. But with the core axioms, we can actually handle quite a lot of the typical situations. So we take all this data, and the problem with the future, of course, is that what we look for is an infinite tree. And in this infinite tree, we look for a finite sequence of things. in general, this is a semi-decidable problem because we know that if there is a finite sequence, we will find it in finite time. But what happens if there is no finite sequence? Then there's no real boundary to actually find it. So what we at the same time, this problem is limited because of our language. You cannot do arbitrary things with our language. It's quite powerful, but it's also restricted in an interesting way. And so what we do here, we translate it to colored patronets. I don't want to go into patronet theory here, but if you want to catch me later, I can do a little bit. Not an expert. Christoph, who's done most of the work on this for his PhD thesis, would tell you better, but I can tell you a few things of what we have done in order to achieve this. And the nice thing about colored patronets is that they are very expressive, and you can exactly ask questions like, is a particular state in the future reachable? Even if you have an infinitely long future. Of course, you cannot allow arbitrary computation, but our model does not allow for arbitrary computation and is still yet rather expressive. And then we can describe the problem as a reachability problem in this colored patronet. So we know this is now the right step to do, and this, of course, should not be done. For the latter one, there is no destiny. So this lets me conclude. What I've tried to convey here is that access rights are necessary, important, needed, but you need more. You want to have a little bit more flexible handling of your data and then tie that to access rights. You want to have something like business rules that say, if you have patient data, no matter what you do, all the time, you should not give it to the senator, for example, but you should give it to, you may give it to a physician or nurse, stuff like that. What you need here is information about what has happened in the past, quite often for practical reasons. You could, of course, do without and then think about some very complex machinery of putting all these past actions into specific functions, but we think that's less transparent than just taking the provenance. Then finally what we do is we extend the provenance graph into the future to think about what's happening. And then of course the clue here is that we achieve a decidable decision problem to give you a hint about the obligations that are to be met. And our language is formal, so it's clear when you write things down what the result of that will be. So thank you. And just a note, most of the work has been done by my PhD student. Not my PhD student anymore because he got his PhD. But so thanks to Christoph.
Thank you. A question as with transition speakers?
Do you have some kind of real-world application for what you're using?
So the whole thing was motivated actually by looking at service-oriented architectures in companies, but the system as it was built now does not have a real application. So we have built the system, but if you have a nice use case, we can put it in there. That would be great.
Sorry. One use case would be an average EU project in science. I'm working now on ToxBank, which is within a cluster of SERAT, safety evaluations, ultimately replacing animal testing, and so it's a lot of sensitive data and a lot of things where I think we could use this very much. How easy, how hard would it be to apply this to a complex network with tens of partners and a couple of hundred of scientists?
I mean, so far the result is the result of a PhD thesis. It's not a hardened system. So it would take still research to bring it from the result of a PhD thesis up to the next level where you apply it operationally. So doing this would be very interesting for us, but we haven't done it.
Some of these systems integrate cryptographic primitives into the kind of language of how things progress. Have you looked at those at all? So that as the information flows from passing to person, you include primitives to sign elements and encrypt data and decrypt data and pass keys around and so on. Have you looked at those?
So the work we did started actually with tracking the provenance across distributed systems. So we can do this. We took a JBoss server and captured things that were happening, events that were sent there. To do the logging, we did a decentralized logging. We could also do a centralized one, which if you can do it, it's much easier and less overhead. That was the foundation, so to say. And then there you have quite a couple of interesting problems. For example, you want to also encrypt the provenance information because the provenance may tell you, for example, whether someone has done an HIV test or not. Maybe you don't want to publicize that. And so there are these issues. So maybe you want to encrypt things. We have not worked on the API level where you would do encryption and things like that, because we really focused then on how to handle these rules and do them at a level that we would consider appropriate. For an end user, I think they're still a little bit too low level, but I think they're already pretty close to some level as you have in typical email systems, where you specify permit or deny rules. And I think they translate very easily to that. It's still a bit more because you have these ordering information that's added here, like the after operator and some other ones.
Okay.
Thank you. So now we have the last talk of this session. And this is a talk by Tim Finin from Maryland University. Go ahead.
Thank you. Well, good afternoon. My name is Tim Finin. I'm from the University of Maryland in Baltimore County. And I'm going to be talking about some work. Mostly it's ongoing in our lab and is the basis of 2 PhD dissertations. And it's on how to make it easier to share data using the semantic web. And start out with a few comments that, of course, data is very important for most science. A couple of comments. We can do a lot more if we share and reuse and build on other people's data. Sharing also fosters collaboration, and its access to shared data is essential for scientific integrity and reproducibility. And just as an example, we're all familiar with the controversy over global warming, and there was this famous hockey stick graph that showed how the Earth is warming considerably since about 1900. But it was controversial. Some people didn't believe it. But the data was shared, and there have been a lot of studies since this original graph that, almost all replicated the phenomena that the Earth seems to be warming. A few more comments that, where does data come from? Well, a lot of it comes from the scientists themselves, but also governments produce data that's useful for science as well as companies. And even there's data being generated by citizen scientists in a lot of fields, and some data just produced by ordinary citizens turns out also to be useful for science. An example of the first category, citizen scientists, we've done some work in the past 5 or 6 years or so in trying to help the field of ecoinformatics capture data from citizens and citizen scientists that they can find useful. So one tool we built was a plugin for Firefox that allowed bloggers who like to go out into nature and talk about the animals and plants that they observed, make annotations to their blog that would include scientific data and get published as RDF that could be then harvested and used. The second example had to do with things called bioblitzes. These are kind of worldwide events where scientists, biologists, ecologists, as well as ordinary citizens, on a particular day will go out and try to catalog all the wildlife and in some cases plants that they've seen in some area, which might be their backyard or might be a park. So it's a kind of an ad hoc survey. And we produced a tool that would allow these people to put the data on their findings in a spreadsheet, and then this would actually get turned into RDF data and collected. So a third example where data from ordinary citizens is useful is the following. During the Gulf oil spill, a lot of people in that part of the country, of the US, were blogging or tweeting about things they saw relative to the oil spill, seeing a tar ball on the beach, seeing some evidence on the beach. So what we did is we mined this data, after the fact actually, from Twitter and from Facebook, and used this to create boundary conditions that were then used on a model from NOAA to predict the spread of the oil. So we found after the fact that had this data been collected and used as it was being generated, the oil spill trajectory predictions would have been more accurate. Here's an example of where we find all these predictions, and had we been able to put those in as boundary conditions into the model, it would have been a little more accurate. All right, so there are a lot of barriers to sharing data. A lot of them have been mentioned today already. There's competition, legal concerns, intellectual property concerns, provenance, trust, privacy, security, et cetera. But the work I'm talking about will focus on one barrier, which maybe is not as big as some of these others, but is important nonetheless, which is that you can't fully exploit or use shared data unless you understand its meaning and can integrate it with your own data. So the semantic web offers solution or a set of solutions that can address this problem, including shared semantic models or ontologies and web standards and protocols to make it easier to find this stuff collected, integrated, and so forth. All right, so a little bit of background on the semantic web just to sort of frame this, although you've seen some of this story before. Eventually I'll remember what my Apple password is and turn that darn thing off. The semantic web really got started in around 1997. And the vision was that of Tim Berners-Lee's, that semantic web technologies will allow machines to share data and knowledge using common web languages and protocols. About 10 years later, this idea developed of creating linked open data, which tried to interlink data sets to better support integration and fusion of knowledge. And from this humble beginning, every year it grew and grew, doubling or tripling every year, until today it's got about 300 different data sets that are part of this somewhat integrated cloud, representing about 31 billion facts. That's a lot of knowledge. And the way I think of it is linked open data cloud is the new psych. If you've been around for a few years, you remember psych, this wonderful vision that Doug Lynott had starting in the mid-'80s of having a common sense knowledge base that could be the center of lots of other knowledge bases and help with integration. And that's what the linked open data cloud has become. And notice that DBpedia, the sort of RDF semantic web representation of some of the content of Wikipedia, or most of the content of Wikipedia, is right there in the middle, and it's kind of an integrating factor. So maybe DBpedia is almost like the new psych, but all these other things around really contribute to it a great deal as well. So linked open data, which we've heard a lot of about today, is really kind of, I think, where the action is in the semantic web field today. Not all the action, but a lot of it. But being able to use and to exploit it is still a little bit challenging, especially for people who aren't, computer semantic web researchers. Two difficulties that I'll talk about today and focus on are, one, it's hard to really query linked open data for an average person. It's hard for me to query linked open data. We'll talk more about this a little bit later. And that means it's hard to sort of really understand whether the answers to the kind of questions you might have are in this linked open data cloud. The second problem is that it's hard to publish data as linked open data. It's easy enough to mangle your relational databases or spreadsheets into RDF, but it doesn't make them 5-star linked open data. We'll talk a little bit more about that later. So we've got two projects that are trying to tackle each of these two problems. So the first one is how to generate linked open data from tables by inferring the semantics of what they mean. And I'm not just talking about relational databases. In fact, I'm not really talking about relational databases at all. But suppose I give you a spreadsheet, or suppose you find a table on the web, or suppose you look inside a document and see a table there. Oh, here's a little table. Used to be in my Blackboard a couple of years ago. What do we know what this, how do we figure out what this means? Well, most people, at least in the United States, most maybe men in the United States, maybe, I don't know, would look at this and figure out what it means. What we want to be able to do is to link these different parts of the tables to things in the linked open data set. And actually, I'll just focus on DBpedia, because that's the use case we're focusing on. And really, that's a good example, a good sample, a good stereotypical example of linked open data. So this team here refers to, ultimately, to National Basketball Association teams. And we also want to link the cell values that represent instances to individual entities in the linked open data cloud if they exist. So this one here, Allen Iverson, represents a particular person who is in Wikipedia and therefore in DBpedia. Well, we also want to figure out what relationships this table represents. It could represent many different relationships. And here, we may hopefully can recognize that this is a relationship that is in DBpedia already that links a professional athlete to the team that they play for. And that's its notation, in the short form, how you might refer to it in DBpedia. And finally, we've got this column of numbers here. It's a little harder to link those because these things are not strings. We can't do entity recognition or something. But we want to get techniques that can figure out that, oh, these numbers represent the height of players in meters, as opposed to something else. All right, so that's our goal. And when we say linked open data here, we're in practice, what we're working with is DBpedia, but we believe that the results are extensible with a lot of work to a larger collection of linked open data. And then ultimately, we take this table and output a file of RDF that represents this file as linked open data. And Tim Berners-Lee defined this sort of rating system for linked open data, and we don't want to have any strings in there unless that's what's really meant. So if you see Alvin Iverson, you say, oh, I know, that's a reference to the entity, this entity over here in our knowledge base. And that's our goal. Oh, why the focus on tables? Well, tables are everywhere. A recent study at Google found 154 million tables on the web that represented high-quality relational data. And nonetheless, even though tables are kind of structured, in some ways it makes them easier to understand, in some ways it makes them harder to understand, harder than maybe natural language text. And mostly, if you just ingest a table, a poor machine doesn't know what to make of it. So here's a use case that Barish is using for his PhD thesis. And it's a challenging one, but hopefully it sort of makes this all worthwhile. Reading tables that you find in medical journal articles and trying to interpret what they mean. Why would we want to do that? Well, the motivation is to support evidence-based medicine where you do meta-studies, integrating the results of lots of other studies to come up with an overall image. And so we think a lot of the real data that these journals talk about are in the tables. And if we could successfully, for the medical domain, kind of interpret these things, perhaps with some human corrections after the fact, and put it in RDF, this might make it much easier to do these meta-analyses from published papers. Oh, another motivation is linked open data, government data. We had a good talk about that. That's going on around the world. And even in the US, in the usdata.gov site, there are 400,000 data sets that have been published. But less than 1% of these are in RDF. So again, they're just tables of various kinds published in various formats and difficult to reuse and integrate. So let me describe what we did last year. Yeah, we did a preliminary system to see how feasible it was to take a table and turn it into linked open data. And our framework was we wanted to first predict the class for columns, and then we wanted to link the cells to entities if they did represent entities. And finally, we wanted to then try to see if we could figure out what relationships we could identify in the table. And it's largely a machine learning driven system using some text similarity, using a text knowledge base, and using support vector machines. And we found that we could do pretty well at predicting the column classes, getting about 77% accuracy, and pretty well at linking cell values to entities. An example where we would get something wrong would be there's a column that really referred to nationality, and for some reason we thought military conflict. That's obviously wrong. Something we would count as right is, a human said, oh, that column, that's the birthplace. But, well, we at least said it's a populated place, and so that's sort of right. And in fact, if you look inside the results, you see that the accuracy was much higher for people and places, a little less so for organizations, and much less so for other things. And this kind of aligns with results of named entity recognition in natural language. Accuracy is pretty good for people and places, and a little less so for organizations, and it goes downhill from there. In fact, a lot of the techniques we used were really named entity recognition and then linking dimensions to things in a knowledge base. Well, but that result wasn't as good as we think we can make it, and so we looked at where the errors came from. One source of errors is the fact that we had this sequential system that first did the column headers, then did the cells, and then looked for the relationships. And that sort of let any errors early on kind of cascade and percolate through the system, and results got worse and worse. A second problem is that the kind of heuristics we developed were biased towards predicting the overly general categories for columns as opposed to appropriate specific ones. So, I could have been real lazy and just said everything's a thing, and that would have been completely useless. It wasn't quite that bad, but it was a bit of a problem. Finally, we felt our system wasn't very principled. It was driven by heuristics, and maybe if we had a more principled approach, we could have better accuracy. In particular, since we have multiple sources of evidence, what we wanted to do was kind of jointly integrate them and do the assignment together, which would also give us a more principled way of approaching things. So in the preliminary system, what we did was we used two knowledge sources, DBP and Wikitology, which was a system done by another student, Serene Sayed, who also was an intern at Microsoft and worked with Evelyne. And basically what it would do, it would take, say it was focusing on trying to figure out what Chicago Bulls might mean in the context of this table. The context really is, well, what's the string that's on the column header, if there is a column header. A lot of tables don't have column headers. And also, what are the other values in the row? And those are the things that are most, provide the strongest context for how to interpret Chicago Bulls. And so we would go up against these knowledge sources, and they can produce a list of possible types for this entity and a list of possible entities. And then it's up to us to figure out what it is. And so you get this ranked list. There is an entry for Chicago Bulls in the DBpedia knowledge base. But it also thought maybe it could mean Chicago, the city of Chicago, or the singer Judy Chicago, and so forth. So our new approach is to number one, make this a little more domain independent. So we've got tables, and over here we've got the linked open data cloud and some other knowledge bases, including Wikitology. And what we want to do is generate a probabilistic graphical model for this table, and then use the information we draw out of this queries against these things to come up with this joint assignment inference model to jointly figure out together what's the overall best interpretation of what do these columns mean, what are these entities, should the entities link to, and what might be the possible relationships between them. All right, so here's our joint model. We've got nodes for the columns and the rows, and when we look at a column like this, what does it mean? Well, the column affects how we would interpret each of the elements under it. But also the columns have to be related. The interpretation for each column type is not done independently, and the values across the rows also affect one another. So we end up, for that particular table we started out with, a simple probabilistic graphical model we generate, and it's got these various factor nodes and final combination modes that manage the joint inference to come up with an overall interpretation that maximizes a score. So what are the challenges here? Well, a lot of the challenges we haven't dealt with come from these literals, especially numbers, that don't carry a lot of information as opposed to strings. So you look at these numbers, you think, well, it could be population of cities, or it could be profit in thousands of dollars. And knowing the column header may guide you there, but maybe you don't have a column header, and what? Similarly, these numbers, if you ignore the column header, might be age in years or percents. So one idea we have is that, remember Psych? Psych had these hand-coded rules. I think they were hand-coded. For example, Psych knew that, human beings don't ever live past 120. If you don't, have a literal interpretation of the Bible, they don't ever live beyond 120. But actually, we've got a lot of interesting data we can collect statistics from. So we can go to DBpedia and we could, find all the living people, find their ages, and get a distribution of their age. And that's a lot more useful than just knowing the max is 120. Similarly, for a subclass of people, professional athletes, we can have a different distribution. We think that's a lot more useful, and we can also, work on capturing not just the numbers, but also the measurement, treating them as measurements that have units. And the metric then for deciding what these things might be would be either a possibility or probability that the values are drawn from a particular distribution for a particular class. So we think that's better than Psych, actually. There are other challenges. If we find a document in the context of a paper, we need to use a table. We can use its caption to provide some context. Some of the tables are going to be too big, like there's a table in the data.gov that has over 400,000 rows, so we can sample them. You don't have to look at the whole table. Just look at the first 100 rows, maybe. And obviously, if you want to achieve good accuracy, you may need to get some human input to do that, to provide some advice or reject bad interpretations. But we think this is a feasible problem, and we're happy with our initial results, and we're looking for more. The second problem is kind of the inverse. If you have this linked open data cloud, how do you query it? Well, again, we're just focusing on DBpedia because that's a sort of microcosm for the linked open data set. You can explore by HTML the DBpedia result, but it doesn't tell you everything you want to know. What you really want to be able to do is query it so you know how things integrate. And that turns out to be hard. The query DBpedia, we got a good formal query language, it's Sparkle. But you have to know the RDF model pretty deeply. You have to know Sparkle. You've got to know the ontology terms you want to use. And even in the small DBpedia rationalized ontology, there are 320 classes and 1,600 properties. And so, you can't remember all those things. The scheme is too big. You've also got to know the URIs to refer to individuals. What's the URI I use to refer to Allen Iverson? You got, over like 100 million, people, places, and organization entities in Wikipedia. And plus, there's some heterogeneity of terms. There's place versus populated place. You not only have to know about those things, but what's the difference between those two? I can't remember. So if we were going to expand this to the whole linked open data cloud, 31 billion facts, forget about it. I can't do it. Well, all right, so maybe an answer is a natural language question answering system. That's a great answer, but it's still a research problem, and it's those systems are not quite there yet. So our goal is to come up with a way, or a person with a basic understanding of RDF and linked open data can more easily query a linked open data cloud. We'll use DBpedia as an example to get answers. And we want it to be easy to use, easy to learn, and have reasonably good accuracy. Well, the key idea we're working with is to simplify the problem so it's not full natural language by having a user enter a simple graph, interconnected graph, and then annotate the nodes and edges with natural language terms and phrases. So for example, place, person, book, book, author, person, person born in place, and for the book we'll put some string up there like the Adventures of Tom Sawyer. So the nodes represent entities, the links binary relationships. We get to pick these words we put down here, and also up here. We'll mark some of the nodes with star if we just don't want to see them in the output, and a question mark if we do want to see them in the output. So how do we do this? Well, we do the translation from this graph to a Sparkle query in 3 steps. The first one is to map each of these things, each node and each relationship, based on their label, to a set of possible things they might be in our ontology space. Okay? And we do this using a similarity metric that's based on distributional similarity, latent semantic analysis, and some data from WordNet. And so we get all these long ranked lists. All right. So sometimes they're good and sometimes they're not good. Look at born in. We come up with cylinder bore. Well, that's just the way, we can talk about that later. Here's another example of football players who were born in the same place as the team's president. That's a little bit more complicated query. These queries can get arbitrarily complicated. So the second step is to, since we have possible interpretations of each of these nodes or links, to try to find an interpretation of every one that maximizes the overall goodness of this as a query against our linked open data set. So here we're going to bring into the statistics of the data, right? And the primary measure we're using is pointwise mutual information between the RDF terms and the LOD collection. It's an easy statistic to compute. And that measures the degree to which 2 terms, ontology terms, associate, and we want that to be kind of the same way the 2 natural language terms associate. And a little bit of math behind it. There's a few other steps when we have a relationship. This graph where the user's drawing, we're kind of ignoring the arrow. We're going to figure out which way the arrow runs ourselves. And we're going to look at pairs of node and node, node and link, and try to find good combinations of pieces together. So for the simple example of where was the author of the Adventures of Tom Sawyer born, we noticed that the number 1 interpretation of this node was right, but the number 8 interpretation of that node was right. Number 1 was right here. Number 3 was right, or right being selected by our algorithm, and number 1 was right here. This is a simple case. And so once you've kind of made that determination, it's pretty easy to generate a Sparkle query from it. And all right, so how well does this do, this simple approach? We took 33 questions from a recent workshop on question answering linked open data, and we had human subjects kind of use our system to come up with a query, and then compared the results against 2 systems, PowerAqua and True Knowledge. And our overall accuracy was by far better than PowerAqua and True Knowledge, getting 0.7 for, well, we had 2 different kinds of queries, but approaching 77% for what turned out to be the best way to formulate queries. If you're interested, we have, a rough system going at this site where you can put in, your query. We don't have the graphical user interface built yet. We think, users will like that, but this will let you at least explore the technique, and you can see exactly how you put these things in, and there are a number of sample queries you can try. Also, for a query, you can just look at the answers, or you can actually look at the gory details of all the potential queries our system generated under different kinds of constraints, and you can try running each of those if you want, and look at the preferred queries at each stage of the translation. So again, there are a number of challenges here. The baseline system that we have works well with DBpedia, but extending it to a bigger linked open data collection, we don't know what'll come up there. We need a better web interface. We need a way to allow people to provide some feedback and advice, like, well, no, you got that node wrong, and try again, and here's some advice. This system mostly operates at the T-box, entirely operates at the T-box level, which is why it's fast. It gives responses in under a second. We're not really reasoning over all the assertions, only over the schema level things and schema level statistics. So we know it'll be a lot more accurate if we put in some at least entity matching at the instance level. And finally, the big challenge is how do we extend it to a linked open data collection, and maybe not just the linked open data collection, but you give me a linked open data collection, and then we'll build a query system for it. Again, if you're interested, you can actually try it out there. Okay, so final conclusions, just for the short talk here, is that yeah, scientific data can benefit from sharing. Sharing it as linked open data, which exposes its meaning much more so than any other way. But generating and exploring linked open data collections is challenging. And we think these kind of tools, one, helping you map your table data in a table to linked open data. And number two, giving you a way to use a sort of a semi-natural language query interface to see what's in linked open data, see what terms people are using, will aid someone who's not a pure semantic web researcher and using these kind of techniques. Thank you.
Time for question.
When you look at tables, you're only looking at one dimension, right? So you have population, but you wouldn't have something like population and divided male and female. Or you're not looking into different dimensions into that. Because one of the things we're looking at, sometimes tables are representations of one view of the database, of a data cube. Are you looking into that?
Do you mean like a kind of table that's split in two?
Exactly.
And over both columns it says population, and then
or you could see male and female, and then population and other aspects.
Well, that's one reason why we wanted to look at a specific domain, a medical domain, because when we looked at the tables there, they had all kinds of crazy tables in these articles, and rows have headers, columns have headers. Rows can be split, columns can be split. So we're gonna wade a little bit into that territory because we need to for this domain. But yeah, it's challenging. I have
to restructure and try to define, go back, and try to imagine what is their view of the data cube. What is it they're trying to reconstruct?
Yeah, and I think for some of those tables, having the caption or the text that refers to the table will really help by providing some context. Some of the details of how to interpret the table are in the text.
Using the header as a metadata.
Yeah.
Just a general question about how sparse the tables are and whether that, you said the graphical models don't scale to some of the OpenGov ones, and whether sparseness would help that scale, or you're not taking advantage of it yet? Or
the tables we've looked at are not sparse at all. They're complete tables, I think, for the most part.
And if you had sparse tables, would you need to adjust your techniques, or doesn't it really matter because the way you...
I don't know. That's a good question.
Yeah.
Okay. I think our techniques don't depend on the tables having an entry for every cell, but I don't know.
Okay.
Good question.
Can I ask what you're using to process the graphical models, out of curiosity?
What we're using to
what library of inference code?
I think it's all pretty much done. Well, let's see. Yeah, both students are, well, one student's using Java, the other one's using Java and C and I don't know, C++.
Okay.
Nobody's using F#, actually.
Yeah.
Probably.
And the inference you're doing over the graphical models, which inference technique are you using? Are you using approximate inference techniques over the graphical models?
Harish is going to write his own because the kind of inferencing that we think we need to do isn't directly supported by any of the packages we looked at. We're going to write our own.
Okay, great. Because info.net is this Microsoft research library called info.net is a processing package for graphical models. It might be of interest as a basis for some of this work. And then you can use F#. Well, yeah.
It's a nice follow-up there. Eh? Any other question? All right, thank you very much. And now time for break.